Okay, so we're just gonna do the code then, not the pseudocode. We didn't break it. Okay, so what do we need to start with? So in order to implement this adaptive quadrature, you first need, well, a function to try to estimate. And then, well, a start point and an end point, of course. So instead of using pi half, I've just opted to use pi here. Not sure why. The tolerance is 1 times 1 times 10 to the power of minus 12, so it's fairly small. And here, that's the largest number of levels we can have because, well, since this is a recursive function, you want to give it a hard limit. Because if you don't give the hard limit and one of the other, so if, for instance, if it's impossible to get the tolerance you want, then you need to stop at some kind of limit and then just give an error message that, well, we didn't reach the level of accuracy you wanted, but this is the best we did with the input. So that's why you need two termination conditions. One that you know will always happen and one that you hope will happen. So the tolerance and the, well, deepest level. We can try to play around with that later. Then h here, that's the half length. And then I've just said that fa, that's a function evaluated at point A. fc, that's a function evaluated at point, well, the half point basically, because a plus half the length is the half point. And fb is the other endpoint. And then I've created this, I go into more detail later. So next I've created this function I've called adaptive, and it has a bunch of inputs, which is the function itself and the different function evaluations at different points. And also the endpoint, so this is a start, end, step length, tolerance, also some kind of first estimate of the integral because because it's recursive, so you need to give it some kind of starting value. 0, that's the level you're at, because you need to keep track of the level you're at, and then this is the deepest level you want to go. Okay, so that seems more complicated than the built-in integral function of MATLAB. So integral function A and B, then it does everything by itself. We could have rewritten this so it does everything by itself, but this is how I did it here. Okay, so what we've done here is we've actually calculated the, or approximated the integral on this level up here. That's kind of the input up here. Next, what this will try to do is, well, you go one level down, and then you try to figure out the midpoint of the current interval again. So this is basically the same as h in the first iteration, and then you say that h is the half of h because you're splitting it. Something like this. That's what you're doing. Okay, and then you need to figure out what the left integral is supposed to be. So that's basically you do Simpson on the left side, and then you do Simpson on the right side. So basically just Simpson here with different points. So you are using point FA. So FA in this case will be this point here. Same as this down here. You just split the interval. Then D here, so f of D, that will be the point, the midpoint here, and then f of C, A, B, I call that B, yes, B, of B over here, midpoint here. Try to illustrate here. Basically, you have the full interval, you are given already the integral there. This is I, left, right, out, and then you try to figure out the error. Which is basically just the difference in the left and right minus your estimate for the big one. Okay. I mean, on the notes, I guess I wrote I minus this, so that should be the same. What is stood there. Okay, and then you have to check so that you're not at the deepest allowed level. So in order to avoid infinite recursion, we set a deepest level, basically. And then you want to give an error that, well, we didn't make it. And if not, then you check if the error, one up here, is less than 15 times the tolerance you have. And as we showed with math, then we should have a good estimate. Next, we can do a Richardson extrapolation. Had yesterday. No, not yesterday. A while ago. Anyway, it's a trick to just improve the integral of what you have. Basically, you return the sum of these two, and then you have this Richardson extrapolation or correcting factor, which gives you a better estimate of the integral. There's an extra trick. Okay? If not, then you have to go deeper. Then you have to split your interval again. That means you're splitting these. Again, like so, because you didn't meet the criterion. And you don't have to split both of them. It could be that you only split one of them. But you have to start the process in both of them here. Okay, you sum them, and you basically just continue. So you see, this is just a function, and it calls itself. So adaptive there, and that's also the name of the function, which is what makes it our recursive function. Calls itself. Yes. Mm. Yes. So it could be that when you're trying to go with this, so that's not, it doesn't give you a good enough answer, then you have to split it. But it could be that maybe you don't have to split this side. What do you mean? But you need a full interval to estimate the whole thing. But it could be that your function is more fluctuating on the left side and more calm on the right-hand side. Then you need more intervals on the left-hand side than right-hand side. The thing is, you don't really have to think about this, because you can just use this function. Just call it, and then it would basically just, well, because of math, if this holds, then you're good. As long as this assumption holds, then you're good. Then you're good. Is that an answer for your question? Yeah, good. Okay, so let's try and run it. And we'll see input. So our approximation, basically 2. That's what we're supposed to do. Was supposed to get. I could actually just change this to pi half, so we have. So pi half. Almost. It's supposed to be 1. So this is 9.99999 to the power of 10 to the power of minus 1. So that's almost So you see both our approximation and the MATLAB approximation, they kind of fail, but not really. This is good enough. And you see the target error is this, and the pessimistic error estimates. And here you see the deepest recursion level was 8. So what happens now if you say you are not allowed to go further than 5? Then you should get an error. You get a lot of errors, you see. Deepest level exceeded, and then it just fails because then all of the functions fails because it calls itself so many times. So the error handling here could have been better, of course. Also try to have better tolerance still. Okay, and that's because ours is exactly as here again. It's difficult to say which one is best, but ours work at least. And again, since this is order of or H4, we try to use fourth order polynomial. We should be able to correctly no. Well, almost. We don't have a machine. But it works. But it's fairly decent, and I actually know what's happening. If I just use the MATLAB one, we don't really know what's happening, and you can do more benchmarking here if you are interested. But it's a good exercise to try to get this. At least look at the code and try to understand it. Because recursive functions can actually save you. Okay, then we have one more topic for integration. Unless there are questions. Okay, so I'm going to give some graphs. So up until now, we've always evaluated the function at the end of intervals. So, and if you have a good explanation to why we have always done the end intervals, is this the best way of doing it? Rhetorical question. Here. Okay, so you are given the function here. And I will do a trapezoidal approximation. Integral. Okay, so if I pick the endpoints, I get this. Okay, so is this the best? Can we do better? If we had picked the points there and there, so you see here we always undershoot, but if you pick points further in, we evaluate the function, and we still have this full length of it, of course. Then you see we have both over and under. So the thing is, can we actually figure out a way to find points inside the interval that will give us a better approximation than just picking the endpoints? Well, the answer is yes. I'm going to try to do this. This is called Gaussian quadrature. And it will give you a more accurate result. And I mean, here, the same amount of function evaluations, it's only you've moved the points slightly. And it gives you a better result. Why is this? Well, because math. Or maths. Gaussian quadrature. So what I'm going to posit is that we pick points or choose points in an optimal way. And optimal here is, again, with some restrictions. Want to start with the x be approximately 1 and I of xi. Again, the i's are some kind of weights. So we want this to be to give the exact result for some kind of degree. So this smells of interpolation. Forward. So we're going to assume we want the degree n equals 2. So that's the degree of, well, the polynomial interpolation we'll use here. So a polynomial of degree 2 and interval well, 1 to 1 is the interval. And then we want to determine this C1, C2, 1, and 2. So C1 and C2, those are the weights we give to the function evaluation, and x1 and x2 is the points we're trying to evaluate. Such that one dx C1 of 1 plus 2 of x. This should always, so since n of 2, this should always give the exact result when f is a polynomial of degree 2 or less. Sorry. And three. So we have 2 points, so -1. Okay, since we have kind of 4 points, okay, makes sense. Okay, anyway. So we'll say that the general form of the function f of x is 0 plus 1, 1 plus 2, 2 plus x. So, okay, so if you try to actually integrate this, we should get 0 plus 1 squared squared x, really easy, 0 x plus 1 And you should be able to do these given some kind of Okay, so we can basically just look at one of them. One of them. So if you think yes. Where is that from? Trying to think why it's -1. But you have 2. No, it's 2. Because that's the amount of points we have. So, or variables. It should be times 2. Say 2 times 2. That's 2 to the power of 2. So n to the power of 2. I think that should hold in general. Yes, I don't remember. I'm sorry. Why it's -1. No, I don't remember the detail exactly there. But anyway, have you done polynomial space? Does this tell you anything? Okay, so say you have 3-dimensional space. What can you have to represent 3-dimensional space? You have an x direction, a y direction, and z direction. Okay, so that's given by the vectors 1, 0, 0, 1, 1, and 1, 1, 0. They kind of span. They span R3. Okay, that makes sense. So polynomial space. What is the basis of polynomial space? Yeah, but it's kind of beside my point. It's anyway, this is kind of a basis of a space. So the basis of polynomial space will just be the polynomials. So if I give you 1, x, and x2, that's the basis, or a basis of, if we do x3, then this is the basis of the polynomials of degree of order 3. Because I can construct every polynomial of degree 3 using the system basis function. Okay? So that was a kind of a side note, but if I can show that each of my principal directions in polynomial space fits this, then all of the other possible linear combinations of these should work. Does that make sense? So instead of trying everything at once, I will just go through each of the kind of basis of polynomial space. Okay? So I will first try with 1. So just 1. Then we want to find how to write the way, or the basis 1. Okay? Then we would have -1 to 1, 1, the x 1, 1, 1. This should be equal. That's the integral. For x, dx should have c1 x1 plus c2 x2 to be 0. Integral for an odd function, which x is over a, well, called an odd interval? No. Anyway, it's 0. x2 should give us a positive number. Minus 1 squared dx c1 s1 squared plus c2 squared is third. And last way here, minus 1 to 1, 3 is zero, but c1, x1, c2 should be 0. Okay, so now I've done all of the basis function of D3 or polynomial space 3. And all of these C's are the same. Okay, I could have just done brute force and just done all of this, but that's a lot more writing. The thing is that now we have 4 equations with how many unknowns? 4. We have, so what we want to figure out is C1, C2, X1, and X2. 4 unknowns. And now I have 4 equations to describe them. Can I actually solve it? Yes. So in this case, we see that if C1, 1, 2 is equal to 1 is equal to minus 3 over 3, 2, 3 over 3, then this will actually give us a better integral than just picking the endpoints. If you take a look at the they come from these equations. Yeah, you should basically just solve them. I'm not going to go through that in detail. But you can kind of see that it works. So if C1 and C2, if both of them, well, the sum of them has to be 2. No? So that works here, plus, yeah, 2. Okay, here it's kind of more difficult, but we see that x1, x2 should be the same, but with opposite sign if C1 is equal. And then you can go, well, continue down here. What I was going to say is that if you look at the exam for at least last year, then you have the formula sheet here. Then you have more of these points. So this is only of 2, well, degree of position 3. So you could also have, well, this is polynomial space 3. You could also have higher polynomial spaces to do the interpolation. You will get more equations, more unknowns, more difficult to solve, but you will still get some points. And these weights aren't always 1. They could be something else as well. And they are called Gauss-Legendre points. I'll try to figure out how to do it. But basically, to sum up, an integral from minus 1 to 1 f dx. This is 1 time the function evaluated at 3 over 3 plus 1 times the function evaluated b over 3. with a degree of addition equals 3. Okay, but does this always hold for each and every interval? So my starting interval here is from -1 to 1. What if I asked you to integrate from, let's say, 2 to 5? What would I have to do then? Well, I could just scale my function. I could just a linear scaling of my function, and it works. So you could go either way. You could try to figure out basis of, well, you're going to basically just solve these functions for the interval you're in, because in this interval is from -1 to 1, and then go through all of the basis functions. Or you could try to look over the pre-computed list of weights, C1, C2, and nodal points, the x's, x1 and x2 in this case. They are pre-computed lists of this. And that's what I try to say in the formula sheet. On the XM, there's a list of them. What you want to do if you want to use them, though, is to actually scale your function. So just a linear scaling of your function. You're covered. So a transformation of your function, so to say. But I won't do that here. But in a more general sense, how do we find these points, or these points? I'm also trying to make a point of actually scaling the function, because that was given as a exam question last year, and a lot of people forgot to actually scale the function to the interval -1 to 1. They just said, well, we're going to use this. So I think actually, because some of the points are going to be negative, but the function was only defined from 0 to pi, maybe, if I remember correctly, and then it won't work. And I mean, it's outside your interval. You will get a result, but it's going to be a wrong one. What? I'll find more of them. So we'll assume that's 1, 2, biter, n are the roots of the n Legendre polynomial. Are there any people who speak French here? Legendre, is that the correct pronunciation of it? I think it's Legendre. Sorry for all the writing. For each I 1 to all the way up to n, the weights I are defined by, there we go, Ci, the integral from 1 to 1. J equal 1. J is not equal to I. N J I minus J. Okay, so is this something you want to boot every time? I mean, this is something you do one time and then you look up a list. So this is, if you remember back to the polynomial interpolation, this is similar fashion. Nothing. No, I tried to say that they don't always equal 1. Okay, that's what I tried to say anyway. So if you are given the roots of the Legendre polynomials, if you remember them, they are kind of a basis for polynomial space as well, but they are, well, orthogonal to each other and also length 1, I think. No, not necessarily length 1, but anyway, that doesn't matter. The roots of the Legendre polynomials you have that you can use. No, that's what I'm saying. So, I mean, this is, in essence, it's an easy operation to do. All of you can do multiplication, and all of you can do integration with polynomials. So it's not a difficult task to do. It's just time consuming. It's very time consuming to do. You could always do a program for it, but most often than not, you want to just look up these, and then do a transformation of your function instead. Because yeah, easier that way. So if p of x, so this is not p of n. To n minus 1 to dx equals, well, the sum of sp I ci at xi. Okay, and that's where the 2 times 2 minus 1. So it should be less than 2n. But still, I'm not quite sure why it's supposed to be less than, but if you try to do the math, it should work out. Oop. Then we have 5 minutes and show how to scale this. So say that you have, instead of minus 1 to 1, you have the interval a. Okay, so you do, I think that's a 2. That should get you inside the interval from minus 1 to 1. Or you say that x equals 1/2 b minus a b a plus b. Basically, you have the function a to b f of x dx. Well, now you have to try to apply the transformation. So x here is this 1 to 1. Good. F of half b minus a t plus b minus a over 2 dt. Oh. This bit here, this bit, because you're doing a linear scaling. There, yes. Good. Yeah. Or for the Gauss Legendre, b minus a 2 c I of minus a 2 okay. A b over 2. Where these xi is from the, because then you've also done the transformation of your function. This one you look up in the table. You could also calculate them, but easier to just use the table. Questions? Hmm? 35? I guess. So how do you mean with an example? Basically, just how it works. So say that, well, you have from 0 to 5, like so. So t is for 5, like so. Or what do you mean? So that's going to be your t. If you now try to insert 5, so if x now is 5, you should get 0. Yes. Yes, then it's let's just right. So we have 0 minus 5, so minus 5, 1, 5, 5, 5. Then we have 10 minus 5, so that's 1. So e equals 5 over... Oh, that should be... Not correct. Let me... Could be that. Ah, should be a minus 1. I forgot in the note. Yeah, so this t is correct, maybe. We could try with this one instead. X minus. Yes. Could be some kind of miscalculation in my notes, something. Try with that function instead. See if that works. Anyway, we're running over time, but yes. This one should at least be correct. My notes could have been wrong. It should be the same one.